So today we're going to continue to look at the microstructure of cement paste. What are the major compounds looks like, and what are their mechanical properties and the physical properties. Okay. All right, so this is a review of the previous slides. Remember major compound, okay, C3S, C2S, C3A, and C4AF. Okay. Last time we talked about the hydration equations for this major compound. The gypsum is added to control or slow down the reaction of C3A. Okay. So this is what we discussed last time. And cement hydration will generate a lot of heat. Okay. And cement grain will dissolve, diffuse, and precipitate. The hydration product is precipitated on the surface of cement grain. Okay, so this is again what we discussed last time. Okay, so we have more people joining. Okay. And this is the chemical reaction we discussed last time. C3S, C2S will generate CSH, which is the strongest and most durable hydration product in concrete, and also calcium hydroxide CH. Okay. For C3A, depending on the ratio of C3A and gypsum, you could have ethylene or monosulfide aluminate. Okay. And this is hydration of C4AF, very similar to C3A, but reaction is slower compared with C3A, and it will not cause late ethylene formation, or in other words, sulfide attack. Okay. Okay. So here shows the conceptual view of hydration. So initially we have Portland cement grains, which is black area, mixed with water. Okay. During the hydration process, we have more hydration product produced. Okay. As we can see, the CSH shown here. Right. So the CSH will precipitate on the surface of cement grain. So the cement grain, the black color, black area will shrink. Water is also consumed, okay, and more hydration product, CSH, is produced here. Okay, so this figure just simplifies the hydration process. Other hydration products such as calcium hydroxide and ethylene and monosulfide aluminate are not shown here. So only showed us CSH. The second note shows here for complete hydration, 1 gram of Portland cement PC require around 0.32 to 0.36 gram of water. So that means the volume of cement and water roughly is the same. Okay, because the density of Portland cement is around 3.2. Okay, so the volume of 1 gram of cement will be roughly equal to the volume of 0.32 gram of water. Okay, we also call that equal volume concept. Depending on W over C, W is water, C is for cement. So W over C is we call water to cement ratio. Okay, water to cement ratio is the most important parameters in concrete. Okay, when the water cement ratio is larger than 0.32, all the cement grain will be consumed, depending on the size of cement grain is not too big. Okay, so we have 100% hydration, provided the hydration time is long enough. So all cement will be reacted, some water will be left in. Okay, And eventually this water will evaporate and we have some empty space or pores left. So when the water cement ratio is less or equal to about 0.32, we could also have 100% hydration, but all the water will be consumed or reacted, but we have some cement grain left it. Okay? The black color again is the Portland cement grain. So compare with these two figures, the concrete, the cement paste with lower water cement ratio has less pores. Okay? Less pores means higher strength for concrete and also better durability. So in theory, concrete or cement paste with lower water cement ratio is stronger and more durable. Okay. All right, so here shows the major hydration product. The first one, of course, is calcium silicate hydrate, or CSH. Okay. So CSH, the size is very small. So 1 to 0.1 μm. μm is micrometer. Okay. I take majority of the total solid hydration product. Okay, about 50% or even more. The ratio of calcium oxide and silica oxide is not fixed, depending on many situations. So the ratio is between 1.5 to 2. Okay, so CSH is not a well crystalline material. It's poorly crystalline materials. Sometimes it looks like a gel or reticular network. Okay, so again, no well-defined shape for CSH. It looks very similar to tobermorite. So tobermorite is a natural minerals, okay, as we can see from the picture on the bottom right. Okay. CSH is by far the strongest and the most durable hydration product of Portland cement. So more CSH, the stronger the concrete, and the better durability for the concrete. The second one is calcium hydroxide, or CH. This is also one of the hydration product of C3S and C2S. Okay. It is well-defined crystal materials. The size is much bigger. Okay. 0.01 to 0.1, this is millimeter, not micrometer. Okay. Take about 20 to 25% of the total solid volume. Okay. It has a fixed stoichiometry, okay, CaOH2. Okay. So morphology is hexagonal crystal plates. So it has 6 sides on the calcium hydroxide plate. So again, well-defined crystals. Compared to CSH, calcium hydroxide has lower strength, and it is also soluble in water. So it will reduce the strength and durability of concrete. By using pozzolanic reaction, by adding silica fume, flash, or slag, which I think we discussed in last week. Okay. So we call that pozzolanic reaction. That can transfer calcium hydroxide into CSH. So make the concrete stronger and more durable. So that is the second hydration product. Right. Then let's look at ethylene dye, or AFT. Remember, ethylene dye is one of the potential hydration products for C3A and C4AF. So it is needle-like crystal materials. The size 10 to 0.5 micrometer. So the length of the needle is around 10 micrometer. The diameter of the cross section is about 0.5 micrometer. Together with monosulfide aluminate, EFM, ethylene guide, and EFM take about 15 to 20% of total solid hydrate. So not a major hydration product. The strength of ethylene guide is much lower compared to CSH, even to calcium hydroxide. So it plays a minor role in the structural behavior. And it potentially can cause problems for concrete, such as sulfide attack, okay, which we also briefly discussed last time. Okay. The cross-section of ethylene guide is also hexagonal plate, okay, but the aspect ratio, which is the ratio between the length over the diameter, is much larger. Okay. So that is ethylene guide. Right. The first one is EFM, monosulfide aluminate. It is thin hexagonal plate. Okay. As we can see from here, the scale is 10 micrometer, so the size is also small, similar to ethylene guide. Again, has minor role in structural behavior, much weaker compared to CSH. So it's thin hexagonal plate crystal. All right. And the fifth materials in hydrated cement paste is unhydrated clinker grains. So depending on situations such as the water cement ratio, if the water cement ratio is less than 0.32, we will have unhydrated clinker. So all the water is consumed, we have some leftover clinker. Okay. Or in situations where the cement grain particles is very big. A rule of thumb is if the size is larger than 60 micrometer, then the core of cement grain may not be fully hydrated. Remember, the hydration process means the water need to dissolve the cement grain, and when we have more hydration product precipitated on the surface of cement grain, water need to diffuse inside the inner side of cement grain and dissolve more ions into the solution. As a result, if the particle size is too large, the inside core may not be fully hydrated. Okay. The strength of cement clinker grain is actually very strong, comparable to CSH. So if we have unhydrated cement clinker, that's not a bad thing. That's a good thing because clinker grain is very strong also. Okay. So these are the 5 major hydration products or materials in hydrated cement paste. Then let's look at the different type of waters in cement paste. Okay, so we have 1, 2, 3, 4 type of waters in cement, hydrated cement. The first one is the red cross, or we call interlayer water. The black line is the CSH, the hydration product. CSH is a sheet-like materials. Okay, so the interlayer water is the water between the CSH sheets. Okay, the green cross is here. Okay, interlayer water is very hard to dry, only when the relative humidity RH in the environment below 11%. Okay. The second water is called capillary water, or the water inside the small pores in hydrated cement paste. Okay. So when cement hydrate, we will have more or less pores. Okay. Depending on the size, some of the pores is called capillary pores. Some of them is called entrapped air. Okay. But the capillary pores will have some water inside it, and we call that capillary water. And depending on the size of the pores, okay, when the pore size is larger than 50 nanometer, when the water evaporates from the larger pores, that is fine. Okay. However, when the water in smaller pores, when the pores is between 5 to 50 nanometer evaporate, okay, that will cause shrinkage of concrete. We call that drying shrinkage of concrete. We have lecture on shrinkage of concrete. Okay. Right now, you just remember when water evaporates from small capillary pores, concrete may shrink. Okay, so that is capillary water. The third one is called adsorptive water. Okay, that's the water on the surface of the solid, the hydration product, on the surface of the pores, which is the blue circle here. You see, on the surface of solid. Okay. So adsorptive water can also be evaporated and cause shrinkage of concrete, but the mechanism is different from capillary water. Okay. The last water is called chemically combined water, or the water here, H, the red H, in CSH here. Okay. So chemically combined water is very hard to lose, almost impossible unless you burn the concrete. Okay, so normal heating or drying will not cause chemically combined water to lose. Only concrete under fire, you increase the temperature to around 800 degrees Celsius or higher. Okay. So again, these are the four major types of waters in hydrated cement paste. Okay. We also have different type of voids. Okay. From small to large, we have interlayer space, which is the voids in the CSH gel, or we call that gel voids. Interlayer space is very small, in nanometer level, and it will not affect the strength and durability of concrete. Okay, so that is intrinsic property of CSH gel, very small. Capillary water is in micrometer level. Okay, depending on the pore size, less than 50 nanometer or more than 50 nanometer, that will cause concrete to behave differently. But capillary voids has another name. It's called porosity. Okay. So porosity basically is a volume percentage of these capillary voids in the total solid in a hydrated cement paste. Okay. The more capillary voids, the higher porosity, the strength of concrete will be lower, and concrete will become more permeable and less durable. So more capillary pores is a best thing for concrete. And then we have air voids, which is much larger in millimeter level. Okay. Under air voids, we have two types. We have entrapped air. Okay. So entrapped air is caused by bad compaction of concrete. Maybe you noticed already, when we pour the concrete in the formwork, we also need to compact the concrete, okay, to get rid of this large entrapped air or honeycombing. Okay, make sure the concrete is condensed. If the compaction is not good enough, we could have entrapped air. Okay, the size is pretty large, 3 millimeter. Okay, so entrapped air is bad. Okay, it will cause lower strength, worse durability. Okay, so that's bad for concrete. On the other hand, we have the so-called entrained air, much smaller than in the entrapped air. Entrapped air is put in concrete on purpose. We have one type of chemical admixtures called air entraining agent. If we put entrained air by using air entraining agent to increase the durability of concrete. We make the concrete more resistant to physical or chemical attacks, such as freeze and thawing, sulfate attack, or alkali-acidic reaction. We'll talk about this in much more details in future lectures. Okay. But today, these slides summarize different type of voids in concrete. The picture on the right showing us the capillary pores, which is the black color. The picture is scanning electron microscope of hydrated cement paste. We have some unhydrated green, which is the whitish color. The gray color around the unhydrated green is the hydration product such as CSH. All right, so we have discussed different type of hydration product, from CSH to calcium hydroxide to hydrogen, different type of waters and different type of voids. And here shows the range of dimensions of all these solid and porous in hydrated cement paste. Okay, so entrapped air is in millimeter level. Okay, entrained air is smaller. This is CSH, calcium hydroxide. Capillary walls is in micrometer level or nanometer levels. And then we have the interparticle space between the CSH sheets, which is in nanometer level. So let's further look at the hydration process. And here shows the effect of time. So we have a virtual experiment. So let's say we have 100 cubic centimeter, 100 cc of cement with a water to cement ratio of 0.63. Okay, so from there we can calculate the water, the volume of water. So raw cement is the density of cement, which is 3.14 gram per cc. Okay, density of water is 1 gram per cc. So the volume of water is 200 cc. So initially we have 200 cc of water with 100 cc of cement, the blue color. Okay, so let's see we have, after 7 days, we have 50% hydration complete, which means 50% of the cement grain is reacted. Okay, so we have less blue, we have more hydration product, the green color, and we also have less water. Okay. Remember, we have initial set time and the final set time, which is after 4 to 8 hours. After concrete or cement paste set, the total external volume will not change as much. So the total volume of cement will kept around 300 cc. Okay. And here it just show the total volume of different phases. Okay. Does not mean the total volume shrink to here after 7 days. Okay. So this is some of the confusing point. Okay. Keep in mind. After 28 days, let's say we have 75% of cement grain hydrated, and we have more hydration product, we have less water, we have less pores, and we have less unhydrated cement. Okay. And after 1 year, all the cement grain is consumed. The only thing left is the hydration product and water. So water you will eventually evaporate, so that space will be occupied by the capillary pores. Okay. Again, the total external volume of concrete will not change after cement concrete set. Okay. All right. And here shows us the effect of water to cement ratio. Okay. Again, we consider 100 cc of cement, and we also consider all the cement grain will fully hydrated. Okay. So for complete reaction, we have 200 cc of hydration per that. Remember, for 100% hydration, the volume of cement will be equal to volume of reacted water. Okay, so depending on the water to cement ratio, let's say we have 5 different water to cement ratio from 0.7 to 0.32. Okay, so for 0.32, all the cement grain will just consume all the water. So as a result, we do not have much capillary pores left. There's no capillary pores when the water cement ratio is 0.32. Okay. When the water cement ratio is higher, you can see the hydration product, the green area does not change. However, the capillary pores will increase. So this tells us the higher the water cement ratio, we have more capillary pores. More pores means weaker concrete, the strength of concrete will be weaker, and also the permeability of concrete will be higher. That will translate into lower durability. So the concrete become weaker and less durable when we increase the water to cement ratio. So the conclusion is lower water cement ratio has lower porosity, so that will increase the strength and also make the concrete more durable by reducing the permeability of concrete. All right, here shows the correlation between the porosity, the percentage of the voids, the strength of concrete, and also the permeability. Permeability defined as how easy water and ions, as well as some other materials, can transport inside the concrete. The easier for water to transport inside the concrete, we said the concrete has higher permeability. Okay, permeability is strongly correlated with concrete durability. The lower the permeability, the higher the concrete durability. Okay. So let's look at these two figures. So here shows the capillary porosity. The solid to space ratio actually is equal to 1 minus P. P is the porosity. Okay. The blue line is the strength. The red line is permeability coefficient. Okay. So let's say when we increase the porosity, the strength will going down. Okay. The blue line will go down, okay, from 30 to below 10. When we increase porosity, the permeability will increase. Okay, so by reducing the porosity, the strength will be higher, the permeability will be lower. Okay. So the range for typical capillary porosity is between 0.3 to 0.45. So this range is for normal or typical concrete. The figure on the right is showing us how water to cement ratio and degree of hydration affect the porosity. Or we put it in this way, how the porosity will affect will correlate with water cement ratio and degree of hydration. Okay. So let's say for the fixed water cement ratio, okay, the higher the degree of hydration, the porosity will goes down. Okay, so that makes sense. A higher degree of hydration, we have more hydration product, we have more water consumed, so the porosity will be lower. Okay. But if we keep the degree of hydration constant, let's say 100% degree of hydration, okay, the higher the water cement ratio, the porosity will going up. Okay, this also makes sense. Increased water cement ratio, we have more water. After 100% hydration, the pores will be more. So that means the concrete will be weaker and less durable. Okay, then let's talk about another topic, how we can measure the porosity. So we know porosity is very important, controlling the strength and also the durability of concrete. But how we can measure that? There's many ways to do that. From electrical measurements, measure the electrical resistance of concrete. We can take a picture and study the image. Okay. We could have some other methods such as NMR, or weight loss, or mercury intrusion porosimetry, or even computer simulations. Okay. So at the end of this lecture, we just pick some of these methods to show us how we can measure the porosity and other property of concrete. Okay. This method is called thermogravimetric analysis, or TGA method. Okay, so this is a method perform a sample. Okay. We prepare a sample, dry the sample off, and then we put the sample in the oven. Okay. Inside the oven, we increase the temperature and we monitor the weight of the sample. Okay. So over time, we know at a certain temperature how much weight loss the sample will experience. Because for certain type of chemicals, that chemical will evaporate or translate into gas at a certain temperature. For example, for calcium hydroxide, it will decompose at, for example, 800 degrees Celsius. If during this test, we found out at 800 degrees, we have certain amount of weight loss. So that weight loss will be the weight of calcium hydroxide. Okay. So based on this concept, we can somehow study the porosity of the concrete. Mercury intrusion porosimetry is another method we can use to study the porosity and even pore size of the concrete. Okay. Mercury intrusion porosimetry, or we call that MIP method, is not the focus of this class, but let me just briefly showing how this method will work. Okay. Okay. All right. So I hope you can see my iPad screen. Okay. So for mercury intrusion porosimetry, we have a container, a glass container. The sample is pre-dried and put inside this glass container. Okay. And then we fill the sample, the container with mercury. So mercury is liquid metal, as we know. Okay. And then we apply pressure, okay, from low to high, could be very high, more than hundreds of megapascal. So we increase pressure and we monitor how much mercury is pushed into the sample. Okay, the sample is pre-dried. Okay, and the pores are empty. Okay, the pore size are varied from small to large. Okay, so we push the mercury inside the sample. Okay, and we can get a curve something like this. Okay, this is pressure, and this is penetrated volume of mercury. Okay, so we increase the pressure, we have more and more mercury penetrated into the sample. Okay, and the volume of the mercury, as you can imagine, is equal to the volume of the pores. Okay, so the valve cell can be easily translated into the pore volume, the volume of the pores. And the pressure has strong correlation with the size of the pore. Okay, so based on equation called Washburn equation, so you don't need to remember the name. So we have correlation between the pressure and the size of the pores. So basically, the smaller the pore size, we need higher pressure to push mercury into the pores. Okay, so from this curve, we can have another curve, which is pore size versus pore volume. Okay, and from there, we can know what is the porosity, how much volume of the pores in our sample, as well as for certain pore size, what are the pore volume. We also call that pore size distribution. Okay, so MIP is a powerful method we can use to study the microstructure of cement and also other materials. Okay, this is not the focus of this class. In graduate level class CEE375, which will be delivered every spring semester, we will discuss in details of different type of microstructure analysis method, including MIP. Okay. Okay. So this is MIP method. Okay. We can also use image analysis method. We can take a picture of cement clinker. So this is cement clinker, and based on the color and the shape of different compound, okay, we know, for example, this is C2S. The dark color round materials is C2S. The light color angular shape materials is C3S. Okay? And everything in between is mixture of C3 and C4AF. Okay? The picture on the middle and on the lower right is a picture of scanning electron microscope picture of hydrated cement paste. Okay. The dark color here is the pores. Okay. The black color is pores. These are the hydration product. The needle are etching guides. Okay. So based on this picture, we can roughly estimate how much pores inside the hydrated cement paste. Okay. The scale is 30 micrometer. Didn't see the scale. So in micrometer level anyway. This is another sample. Again, the black color is pores, empty pores. The white color is unhydrated cement. The gray color is hydration product, including CSH and etching dye. Okay. So based on the picture, we can also estimate the porosity. We can also use computer simulation. Okay. The picture on the left showing us NIST model. So NIST is called National Institute of Standard and Testing. So this is the government agency in Washington, D.C. Okay. And also the DEFT model. So DEFT model is developed by researcher at Delft University, which is the university in Holland, Netherlands. Okay, so let's look at these two models. So this is the model from Delft University. Okay, it simulates the hydration process of cement. So the gray color is cement particles with different size. Water is everything in between. Okay. So we have more. The yellow color is hydration. I believe it's water. The red color, as you can see, is the hydration product precipitate on the surface of the cement grain. So these are the free software. You can Google it and play with the model. You can input information such as what is the water cement ratio, how many days you want this simulation to run, or even some other advanced parameters such as how much pozzolan you put in your system. Okay, alpha is degree of hydration, or how much the percentage of cement hydrated. Okay. So this is the model from NIST.
Particles of cement are arranged on a computer display. The computer determines regions of the particles that can dissolve into water. The bits of dissolved cement diffuse through the water in a random manner and react to form solid phases according to certain rules. After a cycle of dissolution, diffusion, and precipitation is complete, the computer proceeds with another cycle. As this process repeats again and again, the microstructure develops, building bridges between particles that provide strength to material. Computer simulation has proved valuable because it allows researchers to test conditions and make measurements that are difficult to achieve in real life. At the end of the hydration simulation, the structure of the hardened cement paste is very similar to that observed under the microscope.
Right, so this is the NIST model, a NIST model, talk about the hydration process. Again, the three words: dissolve, diffuse, and precipitate, which we discussed last time. Okay, so spend some time to make sure you understand the hydration process. Okay, so that's the NIST model. Okay, so the key idea for this class is what is the size of different hydration products, such as CSH, ethylene dye, calcium hydroxide, monosulfide aluminate, different type of voids, okay, different type of water, and how different water cement ratio will affect the microstructure of concrete and cement, as well as other properties. Okay. All right, that's the end for this lecture. Okay. If you have any questions, please let me know. If not, I'm gonna see you on Wednesday next week. So Monday next week is holiday, Labor Day. Enjoy your holiday, and see you 7 days later. Thank you.